100,000 light-years. The number is not a distance, it is a declaration. It is a judgment handed down by the fundamental architecture of the cosmos to a species of curious primates who have only just managed to escape the thin blue shell of their own atmosphere. To utter the phrase is simple, a brief exhalation of sound. To truly comprehend it, however, is to invite a specific and terrible form of cognitive vertigo, a dizzying sense of scale that threatens to sever the human mind from the comfortable terrestrial anchors of its own experience. A single light year, the gulf that a particle of light will cross in a full terrestrial year of relentless, unimpeded flight, is a chasm of nearly 6 trillion miles. Our fastest, most ambitious robotic emissary, the Voyager 1 probe, would require more than 75,000 years of silent, lonely coasting to traverse such a void. And our galaxy, our own small, local, and seemingly unremarkable island of stars, is a sprawling archipelago of 100,000 of these chasms laid end to end. It is 100,000 years of travel moving at the absolute inviolable speed limit of the universe, simply to cross from one fringe of our cosmic home to the other. This is not a frontier. A frontier, by its very definition, is a boundary that can be reached and with sufficient effort crossed. It is a challenge that beckons to the bold, a problem that can be solved with greater ingenuity, more powerful machines, more time. The space between the stars is not a frontier, it is a wall. It is a final, absolute and non-negotiable barrier to entry, a quarantine enforced by the very laws of physics that govern our existence and permit our consciousness. We are a species born into a prison of such magnificent, beautiful and inescapable proportions that for the vast majority of our history, we have mistaken its impenetrable walls for a decorative ceiling. We have spun tales of galactic empires, of star-spanning federations, of a great and bustling cosmic community waiting just beyond our doorstep, a society we are destined to one day join. Our art, our literature, our most cherished myths of the future are a testament to this deep, abiding and fundamentally human hope. But the universe is not a human institution. It does not grade on a curve. It does not care for our hopes. The universe cares only for its rules, and its rules, when examined with the cold, unforgiving and mathematical eye of science, paint a picture not of a hopeful frontier waiting to be settled, but of a permanent and profound isolation. Interstellar travel is not merely difficult. It is not an engineering challenge waiting for a cleverer, more advanced generation to solve. For all practical purposes, it is a fundamental impossibility, a beautiful dream that is systematically and brutally shattered by the very nature of reality itself. This bleak and terrible realization is the most direct and parsimonious answer to the question that haunts our search for cosmic companionship. The Fermi paradox, the great silence from the stars, ceases to be a mystery of alien sociology or a dark warning of universal self-destruction. It becomes a simple, brutal matter of cosmic logistics. The reason no one has ever visited us is the same reason we will, in all likelihood, never visit them. The reason the sky is not filled with the overlapping radio chatter of a million alien worlds is the same reason our own faint electronic whispers will dissipate into the background static of the cosmos long before they ever reach another listening ear. The yawning gap between the stars is not just empty space, it is a graveyard of ambition. It is the final resting place for the dreams of every technological civilization on every world that has ever harbored them in the 13.8 billion year history of the universe. They too would have looked up at their own night skies with their own unique constellations and their own alien mythologies, and they would have felt the same primal evolutionary urge to explore, to expand, to know what lies beyond the horizon. And then, as their science matured, they too would have done the math. They would have discovered, as we are now discovering with a mounting sense of dread, the series of great unbreachable walls that the universe has erected to keep its intelligent children confined to their nurseries. The first, the highest, and the most absolute of these walls is not constructed of matter or of energy. It is woven with mathematical perfection into the very fabric of space-time itself. It is the ultimate cosmic speed limit, the law that governs everything and pardons nothing, the speed of light. The speed of light in a vacuum, a universal constant represented by the elegant and unassuming letter c, is arguably the most famous and most consequential number in all of science. It is a velocity of approximately 186,282 miles per second, a speed so extreme that a beam of light can circumnavigate the entire globe more than 7 times in the time it takes a human eye to blink. For most of our history, we intuitively understood speed as a limitless quantity. If you want to go faster, you simply apply more force, you build a more powerful engine. There was no ultimate finish line, no final barrier to velocity. Then, in the quiet solitude of a Swiss patent office in the year 1905, a young and unknown physicist named Albert Einstein systematically dismantled that intuition forever. In his theory of special relativity, he revealed that, quote, is not merely a speed at which light happens to travel, it is a fundamental property of the universe's operating system. It is the speed of causality itself. It is the absolute maximum velocity at which any information, any interaction, any influence, any effect can propagate from one point in space to another. It is the universe's own internal processing speed, and nothing can outrun it. The reason for this ultimate speed limit is as elegant as it is profound. As an object with mass is accelerated, its kinetic energy increases. But Einstein's most famous equation, E equals mc squared, revealed that mass and energy are not separate entities. They are two sides of the same fundamental coin, interconvertible forms of the same underlying substance. As you pour more and more energy into an object to accelerate it, some of that energy is converted into motion, but a portion of it is also converted into mass. The object literally gets heavier, more massive, as it approaches the speed of light. This increase in relativistic mass is utterly negligible at the speeds of our everyday experience, but as you get closer and closer to c, the effect becomes dramatic and then infinite. To accelerate a single grain of sand to 99.999% of the speed of light would require a colossal but finite amount of energy. But to make that final infinitesimal push to reach 100% of the speed of light would require an infinite amount of energy, because at that precise speed, the grain of sand's mass would have become infinite. It would contain the mass energy of the entire universe. The cosmos itself, through its own internal logic, forbids such an absurdity. It is crucial to understand that this is not a technological problem awaiting a future solution. We cannot invent a clever new engine that breaks the light barrier any more than we can invent a new form of geometry where the interior angles of a triangle add up to 500 degrees. It is a fundamental axiomatic law of the reality we inhabit. The speed of light is not a goal to be reached. It is an asymptote, a mathematical limit to be forever approached but never, ever touched. It is a cosmic horizon that recedes from us at the very velocity with which we attempt to chase it. This single immutable fact of nature is the first and most decisive nail in the coffin of interstellar travel. It establishes the fundamental timescale of any potential journey. It means that the voyage to even the very nearest stars is not a matter of weeks or months, as our fiction has led us to believe, but a journey of many years at the absolute minimum. The journey to the center of our own galaxy is a journey of 25,000 years, one way, no exceptions. And the journey to our nearest galactic neighbors, such as the Andromeda galaxy, is a journey of 2.5 million years. a span of time so vast that the species Homo sapiens did not exist when such a journey would have had to begin. The universe, in its very first clause, has declared that its constituent islands of matter will remain forever separated by uncrossable oceans of time. The immutable speed of light erects the first great wall of our cosmic prison, a wall of time that defines the sheer, soul-crushing duration of any potential interstellar voyage. But even if we were to accept this grim reality, even if we were to resign ourselves to multi-generational odysseys that last for centuries or millennia, we would then crash headfirst into the second Great Wall, a barrier not of time, but of pure brute force energy. This is where Einstein's equation E equals mc squared returns to haunt us, not as a theoretical limit on velocity, but as a practical and utterly insurmountable economic problem. The energy required to accelerate any macroscopic object to a significant fraction of the speed of light is not just large, it is an amount of energy so stupendously, so astronomically vast, so far beyond our current or any conceivable future industrial capabilities, that it pushes the entire concept of interstellar travel from the realm of difficult engineering into the realm of pure, unadulterated fantasy. Let us perform a simple back-of-the-envelope calculation to illustrate the scale of this barrier. Let us first consider a modest proposal, not a giant, city-sized colony ship carrying thousands of people, but a small, unmanned robotic probe with a mass roughly equivalent to one of our Voyager spacecraft, a few thousand kilograms. And let us set a seemingly modest goal to accelerate this probe to just 10% of the speed of light. This is a velocity that, while impressive by terrestrial standards, would still require a 43-year journey to reach our nearest stellar neighbor, Proxima Centauri. The kinetic energy required to achieve this speed can be calculated with simple Newtonian physics. The number that emerges from that calculation is a monster. It is approximately 200 quadrillion joules of energy. This is a number so large that it is effectively meaningless without a familiar context. So let us provide one. This amount of energy is equivalent to the entire combined energy consumption of all of human civilization, from every power plant, every car, every factory, every light bulb on Earth, for more than 3 full days. This is the staggering energy cost to launch one single small one-way robotic probe on a 43-year trip to the very nearest star. Now let us scale up our ambition. Let us imagine the archetypal vessel of science fiction, a generation ship, a vessel large enough to carry a few hundred human colonists, and the complex closed-loop ecosystem required to keep them alive for centuries of travel. Such a ship, let us call it the Ark, would need to have a mass of at least 1 million tons to be even remotely feasible. Let us again set our modest goal of accelerating this Ark to just 10% of the speed of light. The energy required to accelerate this vessel to that speed is not just larger, it is catastrophically civilization-endingly larger. It would be equivalent to the entire energy output of the human race at its current levels for more than 5,000 years. To build and launch a single such vessel would require humanity to dedicate its entire industrial, economic, and energy infrastructure for the entire span of its recorded history, from the first Sumerian cities to the present day, to this one single monumental project. It is an investment so disproportionate, so all-consuming, that it borders on the absurd. And 10% of the speed of light is, in galactic terms, a pathetic, leisurely crawl. It still means a journey of 10,000 years to reach a star that is just 1,000 light-years away, a tiny, insignificant fraction of the distance across our own galaxy. What if we wanted to go faster? What if we aimed for 90% of the speed of light, a velocity that would finally allow for journeys across the local stellar neighborhood in a matter of decades rather than millennia? Because of bizarre effects of special relativity, the energy requirements do not scale linearly with velocity, they scale exponentially. The energy needed to get our million-ton arc to 90% of C would be equivalent to the entire energy output of the Sun itself for several minutes. It would be an amount of energy comparable to the detonation of a supernova. A civilization would have to achieve complete mastery over the energy of its own star to become a Kardashev Type II civilization simply to launch a single one-way voyage to a nearby destination. The energy wall constructed by the simple and elegant physics of E equals mc squared is so high and so steep that it effectively makes the price of a ticket to the stars the price of a star itself. No sane, rational civilization, no matter how advanced, would ever pay such a price. They would look at the staggering bill and, like any sensible economist, conclude that there are far better, far more efficient, and far more meaningful ways to spend the energy of a sun than to fire a tiny metal can across an empty void. But the horror story of interstellar economics and physics does not end with the sheer brute force energy requirements. It is compounded by a third, and perhaps more insidious and intellectually elegant barrier, the absolute tyranny of the rocket equation. Formulated by the brilliant and visionary Russian scientist Konstantin Tsiolkovsky at the very dawn of the 20th century, the rocket equation is the mathematical embodiment of a cruel and recursive cosmic joke. It governs the fundamental relationship between a rocket's final change in velocity, the efficiency of its engine, and the ratio of its initial mass, including fuel, to its final mass after the fuel is burned. The equation is a recursive nightmare, a snake that is perpetually and ravenously eating its own tail. In its simplest form, it states that to achieve a certain acceleration, a rocket must expel propellant in the opposite direction. But that propellant itself has mass. So to accelerate the propellant that you are about to burn, you need to carry even more propellant. And to accelerate that additional propellant, you need to carry still more propellant. For the chemical rockets that have successfully taken us to the Moon and to the outer planets of our solar system, this equation is already a brutal and demanding master. The colossal Saturn V rocket that sent the Apollo astronauts on their way to the Moon was over 95% fuel by weight. Only a tiny, almost insignificant fraction of its 3,000-ton launch mass was the actual payload, the command module, and the lunar lander that carried the 3 astronauts. The rest was just the fuel and the massive tanks and engines required to lift the fuel. For interstellar travel, where the required final velocities are not thousands of miles per hour but hundreds of millions of miles per hour, the rocket equation transforms from a demanding master into an absolute laughing and insurmountable tyrant. Let us imagine for a moment that we have a perfect engine, a fusion rocket, a technology that is still relegated to the realm of science fiction but is in principle theoretically possible. A fusion rocket harnessing the power of the stars themselves would be thousands of times more efficient than our best chemical rockets. Even with this miracle engine to accelerate a spacecraft to just 10% of the speed of light, the rocket equation dictates that the vast, overwhelming majority of the ship's initial mass must be composed of fusion fuel. For every single ton of payload, the ship itself, the crew, the life support systems, the scientific instruments, you would need to start with thousands of tons of fuel. The ship would not be a vessel with a fuel tank. It would be a colossal galaxy-sized fuel tank with a tiny, almost invisible speck of a payload attached to the front. And this nightmarish calculation assumes you only want to accelerate. If you ever intend to slow down at your destination, a rather crucial step, if you don't want to streak through the target solar system in a matter of hours, you have to perform the entire monstrous acceleration in reverse. This means you have to carry all the fuel needed for deceleration with you from the very beginning of the journey. This squares the already impossible numbers. The fuel you are carrying at the start now needs to accelerate the deceleration fuel. The tyranny becomes exponential. Even the most exotic, most powerful propulsion system that physics allows the stuff of pure, unadulterated science fiction, an antimatter engine, cannot escape this fundamental trap. Antimatter is the most energy-dense substance theoretically possible. When a particle of matter meets its corresponding particle of antimatter, they annihilate each other, converting 100% of their combined mass into pure energy in accordance with E equals mc squared. It is the perfect rocket fuel. But you would still need an enormous quantity of it, and you would still need to carry the antimatter for slowing down. And the energy required to create just 1 single kilogram of antimatter in a particle accelerator like CERN is, by our current, admittedly inefficient methods, roughly equivalent to the entire annual energy consumption of the planet Earth. The rocket equation is a brick wall of pure mathematics. It tells us that any vehicle that must carry its own fuel is doomed from the start. It is a mathematical proof that the archetypal starship of our dreams, a self-contained, self-powered vessel that roams the galaxy at will, is a physical impossibility. The universe has a strict no-baggage policy for high-speed interstellar travel, and the fuel you need to get there is the heaviest and most impossible baggage of all. Let us for a moment suspend our disbelief and indulge in a profound fantasy. Let us imagine that some far future godlike civilization has by some unknown magic overcome all of these seemingly insurmountable barriers. They have found a way to circumvent the speed of light, perhaps by traveling through a higher dimension. They have harnessed the energy of their entire star to power their magnificent vessel, and they have invented a magical, massless, and infinitely powerful fuel that frees them from the cruel tyranny of the rocket equation. They have built their gleaming starship, they have selected their bravest and most brilliant crew, and they have launched their great and glorious voyage to a star 1,000 light-years away. It is at this moment that they encounter the fourth Great Wall, a barrier that is not one of physics or of engineering, but of the very nature of time itself. It is a barrier that transforms their heroic journey of exploration into a quiet and profound tragedy of irreversible social suicide. This barrier is time dilation. Another of the strange and beautiful consequences of Einstein's theory of special relativity, time dilation, is one of the most bizarre, non-intuitive, and experimentally verified facts about our universe. Time is not a universal, absolute metronome, an impartial river that flows at the same rate for everyone and everything. Time is relative. The faster you move through space, the slower you move through time, relative to a stationary observer. For a clock on a spaceship traveling at a significant fraction of the speed of light, the seconds will tick by more slowly than for a clock that remained behind on its home planet. This is not a mechanical error or a perceptual illusion. It is a fundamental property of the geometry of four-dimensional spacetime. The crew of the starship is not just traveling through space, they are literally traveling into the future of their home world. Let us return to our fantasy ark, now capable of traveling at a blistering 99.9% of the speed of light. They embark on their 1,000 light-year journey to a promising Earth-like planet. From the perspective of the crew on board the ship, thanks to the extreme time dilation at this velocity, the journey might take only 45 years. It is a long but manageable single-generation voyage. They arrive at their destination, a beautiful blue-green world, and they send a message back home to announce their historic success. That message, a beam of radio waves traveling at the speed of light, will take 1,000 years to reach Earth. When it arrives, the Earth that receives it will be 1,045 years in the future from the moment the ship first left. But the tragedy is far deeper and more personal. When the ship itself arrives at its destination, from the perspective of the people on Earth, over 1,000 years will have passed. The civilization that built and launched the ship is a distant historical memory. The friends and family who celebrated its departure have been dust for 950 years. The very language the crew speaks may be an archaic dead tongue. The culture, the politics, the technology, the very values of their home world would be as alien to them as the culture of ancient Rome is to us. The connection is irrevocably and absolutely severed. The very act of high-speed interstellar travel is an act of permanent, irreversible exile. The colonists are not an extension of their home civilization. They are its orphans, ghosts arriving in a future that has long forgotten them. And what if they ever wanted to return? A 45-year journey back to Earth from their perspective would deposit them on a home planet that is now more than 2,000 years in the future from their original departure point. They would be returning not to a home but to a museum, a world that has moved on without them for 2 full millennia. This profound temporal schism makes any form of a cohesive, real-time interstellar civilization an utter impossibility. There can be no trade, no meaningful communication, no shared culture, no political union. There can only be a series of isolated, disconnected, and forever sundered colonies forever separated from their parent world by the impassable one-way gulf of relativistic time. It transforms the noble dream of exploration into an act of profound and selfish abandonment. It is a one-way ticket, not to a new world, but to a state of permanent and total temporal dislocation. Why would any civilization choose to inflict such a strange and lonely fate upon its own people? But the horrors faced by the crew of our fantasy starship are not just psychological, social, and temporal. They are also brutally, relentlessly physical. Even if they could somehow endure the crushing loneliness of their exile and the profound temporal disconnect from their own species, they would first have to survive the journey itself. And the space between the stars, the interstellar medium, is not the gentle, empty void of our imagination. It is a shooting gallery. It is a cosmic microwave oven. It is a space filled with a relentless, invisible, and utterly lethal rain of high-energy radiation. This is the 5th Great Wall, the radiation hell of interstellar space. The primary and most insidious threat comes from a phenomenon known as galactic cosmic rays, or GCRs. These are the nuclei of atoms, mostly protons, the nuclei of hydrogen atoms, but also the much heavier nuclei of elements like helium, carbon, and iron that have been stripped of all their electrons and accelerated to nearly the speed of light by some of the most violent events in the universe, such as supernova explosions or the relativistic jets powered by supermassive black holes. They are tiny subatomic bullets, and they permeate the entire galaxy, a constant isotropic storm of high-energy particles. Here on the surface of the Earth, we live our lives in blissful ignorance of this cosmic bombardment, protected by a multi-layered planetary-scale shield. Our planet's powerful magnetic field deflects the majority of these charged particles, and our thick atmosphere absorbs the rest. A starship in the interstellar void has no such protection. It is a naked, vulnerable target in a perpetual cosmic storm. For a ship traveling at near relativistic speeds, the problem becomes exponentially, terrifyingly worse. The ship is not just sitting in this rain of particles, it is slamming into it at an incredible velocity. From the perspective of the crew inside the GCRs, are not just a gentle isotropic rain, they are a high-energy forward-facing beam of lethal radiation. Each individual proton, each ion nucleus, strikes the hull of the ship with the energy of a macroscopic projectile. These particles will tear through any conventional hull material, shredding the delicate, complex molecular structures of human DNA, causing catastrophic cellular damage, aggressive cancers, irreversible cataracts, and severe degenerative neurological damage. They will degrade the ship's most critical electronic systems, flipping bits in computer memories, causing processors to fail and rendering navigation and life support systems inoperable. Over the course of a long journey, they will slowly but surely erode the very structural integrity of the spacecraft itself through a process called sputtering. The engineering challenge of adequately shielding the crew from this relentless radiation storm is another nearly insurmountable barrier. To effectively block the most energetic ion nuclei in the GCR spectrum, you would need a shield of matter many meters thick, completely encasing the entire habitat module. A shield made of lead or water or some exotic composite material would add a colossal, prohibitive amount of mass to the ship. A 1 million ton ark might require a 10 million ton radiation shield, and this brings us right back to the cruel, laughing and inescapable face of the rocket equation and the energy wall. The enormous mass of the radiation shield requires an exponentially greater amount of fuel to accelerate, which in turn requires a civilization-ending amount of energy to produce and harness. The vicious, self-defeating cycle is complete. Any shield massive enough to be effective at protecting the crew would make the ship too massive to launch. Any ship light enough to launch would be a flying coffin, its crew slowly but inevitably cooked by the relentless, invisible fire of the interstellar medium. And even if by some miracle of future technology a physical shield could be constructed, there is no known material that can shield the human mind against the psychological torment of such a voyage. This is the sixth great wall, the psychological cage. Human beings are the fragile, complex, and highly social products of 4 billion years of evolution on the surface of a single, vibrant, dynamic, and crowded planet. Our minds, our very consciousness, are not designed for millennia of perfect isolation in a sterile, unchanging, and claustrophobic metal box. The psychological stresses of a multi-generational interstellar voyage would be immense, insidious, and likely fatal to the mission's success. The first generation of colonists would depart with a powerful sense of purpose and a living memory of Earth's blue skies and green landscapes. But what of the 10th generation, or the 30th born and raised in the sterile, humming confines of the void, a generation who has never seen a real sky, never felt rain on their skin, never walked on solid ground under an open sun? Their only reality is the hum of the life support systems, the recycled air, the artificially lit corridors, and the cold, unchanging, and utterly alien starfield outside the viewport. How do you maintain a sense of purpose, of social cohesion, of basic sanity across 30 generations of perfect sensory-deprived confinement? The profound, life-altering overview effect, the cognitive shift that our astronauts experience when they see the fragile, beautiful Earth hanging in the void, would be replaced by a crushing and nihilistic void effect. The Earth would first shrink to a faint, unremarkable star among millions, and then, as the ship accelerated, it would disappear from view entirely. The crew would be utterly, totally, and verifiably alone, a single microscopic island of organized matter in an ocean of sterile darkness, so vast and so empty that their own existence would seem like a bizarre and meaningless statistical error. The risk of social collapse, of violent mutinies born from generations of confinement, of the emergence of bizarre cargo cult-like religions centered on a forgotten Earth, or of a simple collective descent into a quiet, hopeless, and generational madness would be overwhelming. We are creatures of a specific, rich and dynamic environment, and that environment is the Earth. To remove us from it for 1,000 years is not an act of noble exploration. It is an act of profound and protracted torture, a psychological experiment on a scale so cruel that no ethical civilization would ever dream of conducting it. At this point in the relentless, cumulative argument, the dedicated advocate for interstellar travel will throw up their hands in a gesture of tactical concession and offer the one seemingly obvious alternative. Fine, they will say, crude travel is impossible for 1,000 different reasons. But we don't need to send our fragile, radiation-sensitive, psychologically unstable biological bodies. We can send our robots. We can send intelligent, durable, and patient probes. This is a sensible and logical suggestion, and it immediately dissolves the most human-centric problems of time, dilation, radiation, shielding for life, and the psychological cage. A robotic probe, an AI-driven emissary, does not care if its journey takes 10,000 years. It does not get cancer from galactic cosmic rays. It does not go mad from the crushing loneliness of the void. But while sending probes is vastly more feasible than sending people, it does not solve the fundamental core problems of interstellar travel. It only makes them slightly less impossible. This is the seventh great wall even for our most advanced, most patient, robotic children. The journey is still too long to be meaningful in any practical sense. A probe, just like a crewed ship, is still irrevocably bound by the ultimate speed limit of light. It is still a helpless victim of the monumental energy wall and the tyrannical rocket equation. While we can certainly build a much smaller and lighter probe than a human colony ship, the energy required to get it to a significant fraction of C remains monumental. The most ambitious real-world project currently conceived in this domain is the Breakthrough Starshot Initiative. This project proposes using a colossal 100-gigawatt ground-based laser array to accelerate a tiny gram-scale nanocraft attached to a gossamer-thin solar sail up to 20% of the speed of light. Even this, a project that is at the very bleeding edge of our technological horizon and would require an energy infrastructure comparable to 100 large nuclear power plants, would still mean a 20-year journey to Proxima Centauri, followed by a 4.2-year wait for any data from its flyby to return to Earth. And this is for the very nearest star, our next-door neighbor. What about a star that is 100 light-years away? The journey for our miraculous nanocraft would be 500 years, and the wait for a signal confirming its arrival would be another 100 years. We would receive a postcard from a world that is 600 years in the past. This is not exploration in the way we dream of it. It is cosmic archaeology. It is a slow, patient, and expensive way of learning about what other solar systems were like long ago. But it is not a way of engaging with a galactic community. By the time we receive a probe's signal that a planet is habitable or even hosts a civilization, the civilization that sent the probe might be extinct. By the time we could send a reply to a signal we received, the civilization that sent it might have destroyed itself. The vast, empty light years between the stars are not just a barrier to physical travel, they are a fundamental barrier to conversation. They impose a time lag so profound that any attempt at interstellar dialogue devolves into a series of disconnected, multi-century monologues. Sending probes is a noble and worthwhile scientific endeavor. It may be the only way we ever get a close-up picture of a planet orbiting another star, but it is not a substitute for travel. It does not solve the fundamental problem of our cosmic isolation. It only serves to confirm its immense and heartbreaking scale. The probes we might one day send are not messages in a bottle sent to a friend on another shore. They are messages thrown into a cosmic ocean of such size that they will likely never be found, with the faint, desperate hope that some unknown intelligence a million years from now might find the bottle washed up on the shores of a long-dead world and wonder for a fleeting moment who we were. It is at this point in the argument, when every practical and even every impractical avenue to the stars has been systematically and logically closed off, that the hopeful dreamer will make their last desperate stand. They will appeal to a higher and as yet unknown authority. They will appeal to a physics that is not yet written. They will utter the two magic words that have powered 1,000 science fiction stories: wormholes and warp drive. These are the great hypothetical loopholes, the fantastical escape clauses in the ironclad contract of our cosmic confinement. They are the staples of our most beloved speculative fiction, the deus ex machina, that allows for the galactic empires and federations of our collective dreams. And they are, for the moment and perhaps forever, nothing more than beautiful, intricate, and ultimately unrealizable mathematical fantasies. This is the eighth great wall, the wall of speculative physics, which promises us a key to our prison that is in all likelihood forged from smoke and wishful thinking. Both wormholes, more formally known as Einstein-Rosen bridges and the Alcubierre warp drive, are in a narrow and highly technical sense theoretically possible. They are legitimate mathematical solutions to the incredibly complex and beautiful field equations of Einstein's theory of general relativity. They do not propose to violate the local speed limit of light, which is impossible. Instead, they propose to cheat to find a clever and elegant way around the law. They are audacious schemes for wrinkling and folding the very fabric of spacetime itself, for creating a topological shortcut from one point in the universe to another. A wormhole would be a tunnel through a higher dimensional space connecting two distant regions of our own universe, allowing for a journey that would take 1,000 years at light speed to be completed in a matter of minutes. An Alcubierre warp drive would work by generating a region of spacetime that is violently compressed in front of a ship and violently expanded behind it. This would create a warp bubble that would ride this self-generated spacetime wave to its destination, arriving faster than light relative to its starting point without ever locally breaking the speed limit within its own bubble. They are breathtakingly elegant and intellectually seductive ideas, but they come with a catch, a list of required ingredients so outlandish, so far removed from any known physics, that they may as well be a form of magic. To create and sustain a stable traversable wormhole, or to generate and control a warp bubble, you need a vast quantity of something called exotic matter. This is a hypothetical form of matter that possesses negative mass, or more precisely, a negative energy density. It is matter that would in effect possess anti-gravity. It would fall up, not down. It would push rather than pull. While the strange and counterintuitive world of quantum mechanics does allow for fleeting microscopic and virtual fluctuations of negative energy to exist in a vacuum for incredibly short periods of time, there is absolutely no evidence that large, stable quantities of such matter can or do exist in our universe. To build a warp drive capable of carrying a small 10-meter ship, you would need a quantity of this negative energy equivalent to the entire mass energy of the planet Jupiter. To build a stable wormhole, you would need even more. We have no idea how to make it. We have no idea if it can be made. Most theoretical physicists suspect that it is a mathematical quirk, a possibility that is allowed by the equations but forbidden by some deeper, as yet unknown law of nature, a chronology protection conjecture that the universe uses to prevent the temporal paradoxes and other absurdities that true faster-than-light travel would inevitably create. To pin our hopes for an interstellar future on the eventual discovery of stable Jupiter-mass quantities of exotic matter is not a scientific prediction. It is an act of pure, unadulterated faith. It is the modern technological equivalent of a medieval peasant trapped in their feudal village by impassable mountains and uncrossable seas, hoping that one day a wizard will appear and gift them a magic carpet. It is a profound confession that the known laws of physics offer no hope, and so we must appeal to a physics of the imagination. But the universe has shown itself time and time again to be more constrained, more elegant, and far less accommodating to our wishes than our fantasies. The beautiful, hope-filled mathematics of warp drives and wormholes are likely to remain where they were born on the blackboard, as a fascinating but ultimately impractical glimpse into the strange and wonderful possibilities of a universe that could have been but is not our own. And so after this long and arduous journey through the known and the unknown, we find ourselves standing before a prison of our own comprehension. We have surveyed its walls, we have tested their strength, and we have found them to be higher, thicker, and more intelligently constructed than we ever dared to imagine. This is the ninth, the final, and the real barrier, the horrifying cumulative and synergistic nature of all the other barriers combined. Interstellar travel is not impossible because of one single easily identifiable insurmountable problem. It is impossible because it is a series of a dozen such problems, each one a fortress in its own right, and each one feeding into and amplifying the others, in a relentless, cascading and self-defeating feedback loop of futility. To go to the stars, you must go incredibly fast. But the speed of light, a law of causality, forbids you from ever going fast enough. To even approach that ultimate speed requires an amount of energy so vast that it defies sanity, an energy budget that is denied to you by the simple, brutal economics of E equals mc squared. To generate the velocity you need with any conceivable engine, you must carry a mountain of fuel that is so heavy that it makes the ship itself impossible to accelerate in the first place, a cruel paradox enforced by the recursive tyranny of the rocket equation. If you could somehow, by magic, solve all of these problems, the very act of traveling at such speeds would permanently and irrevocably sever you from your home world, casting you adrift in time, a tragic and unavoidable consequence of time, dilation. During this journey of temporal and social suicide, your body and your ship would be relentlessly scoured and sterilized by a lethal, invisible storm of cosmic radiation, a storm that you cannot effectively shield against without adding so much mass that the rocket equation and the energy wall return to laugh at your futile efforts once more. And if by some miracle upon miracle your body and your ship survive this onslaught, your mind, the fragile social and evolved product of a single specific world, would almost certainly break under the unbearable strain of millennia of perfect, featureless and absolute isolation in the psychological cage of the void. To escape this, you might choose to send a robot, but the robot is still too slow, its message taking millennia to return a whisper from a long-dead ghost. And so, in your final act of desperation, you might dream of bending spacetime itself, only to find that the price of admission to this final fantasy is a form of magical matter that the universe has, in all likelihood, wisely and prudently chosen not to create. Each of these walls is a fortress. Together they form a cage from which there is no escape. The real barrier is the conspiracy of physics itself. The universe is not designed for travel, it is designed for confinement. The laws of nature seem to have been carefully, precisely, and elegantly constructed to ensure that life, if and when it arises, stays where it began. The stars are not destinations, they are decorations. They are the beautiful, unreachable lights on the ceiling of our shared and permanent cosmic home. We are not a species on the cusp of a great interstellar diaspora. We are, and in all likelihood will forever be, a species of a single solar system. We are stuck here. This is a difficult and for many a deeply unwelcome and pessimistic conclusion. It runs counter to our most cherished myths of endless progress and manifest destiny. It feels like a failure, a cosmic grounding of our species for a crime we did not commit. But perhaps this is the wrong way to look at it. Perhaps this realization, this sober and mature acceptance of our permanent confinement, is not an ending but a new and more meaningful beginning. It is the beginning of a new kind of maturity, a new kind of wisdom, a new kind of civilization. For if we cannot travel to other worlds, then the value of our own world, this one single, beautiful and utterly irreplaceable planet, increases to infinity. This is the final and most profound implication of the impossibility of interstellar travel. Earth is not our cradle, a planetary nursery from which we are destined to one day graduate. It is our final destination. This shift in perspective is the most important one our species may ever have to make. It forces us to abandon the adolescent and dangerous fantasy of escaping our self-inflicted problems by finding a new home. There is no planet B. There is no pristine, empty, and conveniently located Earth waiting for us just a few light years away. We cannot ruin this world through our greed and our short-sightedness, and then simply pack our bags and move on to the next. This is it. This is the whole inheritance. Our destiny is not written in the distant stars. It is written here in the soil, in the water, in the air of this one singular planet. Our great multi-generational project is not the conquest of the galaxy, but the stewardship and preservation of the Earth. Our future will be determined not by the speed of our starships, but by the wisdom of our actions, right here, right now, in this critical and fleeting moment of our history. This realization does not need to be a source of despair. It can be a source of profound and urgent purpose. It imbues our world with a kind of sacredness that no myth or religion has ever conceived. We are living on the most valuable and most precious piece of real estate in the entire galaxy and perhaps the entire universe. It is a living, breathing oasis of impossible luck in an endless sterile desert of frozen rock and lethal radiation. To be born here is to have won a lottery with odds so great they are indistinguishable from a deliberate and benevolent miracle. Our duty, our single great multi-generational purpose, is to protect the prize, to build a civilization that is as stable, as enduring, and as beautiful as the planet that gave it birth. The silence from the stars is not a mystery that needs a solution. It is a lesson that needs to be learned. The reason we hear no one is because the universe is a collection of lonely, isolated islands of life, each one trapped within the confines of its own solar system, each one facing the same ultimate and binary choice to learn to live in harmony with its own finite world or to perish. We are not alone in our challenge. We are only alone in our outcome. The future of the human story will not be a grand sprawling epic written across 1,000 star systems. It will be an intimate, difficult, and beautiful drama played out entirely on this one small and infinitely precious stage. Our final frontier is not the empty space between the stars. It is the challenging space between ourselves. And our greatest and most noble exploration will not be the charting of new and distant worlds, but the charting of a sustainable, peaceful, and meaningful future right here on the only home we or our descendants will ever know. A single star indistinguishable from a billion others vanishes from the night sky. It does not explode in a supernova, a final brilliant shout of stellar death. It does not collapse into a black hole, a gravitational full stop. It simply fades its light slowly and systematically occluded over the course of a century. The fading is smooth, deliberate, and unmistakably artificial. It is the signature of a colossal engineering project, a shell of collectors being assembled around the star to capture every last photon of its output. A civilization is drinking its sun dry. This is not science fiction. It is a logical, predictable step for any species that survives its own technological infancy and continues to expand its energy needs. Yet when we scan the heavens, we see no such projects. We find no stars being methodically dismantled. We detect no fleets of construction drones swarming a stellar system. The sky is quiet. The stars burn with a wild, untamed light. This silence is the heart of a profound and unsettling paradox. Our galaxy, the Milky Way, is ancient. It has existed for over 13 billion years. It contains upwards of 400 billion stars. Many of these stars are much older than our Sun, orbited by planets that have had billions of years of a head start on Earth. In this vast expanse of time and space, the emergence of life, and subsequently intelligence, seems not just possible, but probable. A simple calculation suggests that even with conservative estimates, the galaxy should be teeming with technological civilizations. Some of them should be ancient, their science and engineering advanced beyond our wildest comprehension. The logic is inescapable. If a civilization can arise on one planet, it can arise on many. If one of them survives and continues to grow, it will inevitably expand beyond its home world. The impulse to explore, to acquire resources, and to ensure survival is a powerful driver. Within a few million years, a mere cosmic moment, a single expanding civilization could colonize the entire galaxy. It could send self-replicating probes to nearby star systems. These probes would use local materials to build new colonies and new probes, which would then be sent to the next set of stars. This process would create an exponentially growing wave of colonization, a tide of intelligence washing over the galaxy at a fraction of the speed of light. Even with a slow expansion speed, the entire Milky Way could be settled from end to end in the time it took for mammals to evolve on Earth. So the question is not just, are we alone? It is a much more pressing and specific question. Where is everybody? The great Italian physicist Enrico Fermi famously asked this question over lunch in 1950, and the silence has only deepened in the decades since. The absence of evidence is not just a lack of radio signals. It is a lack of any physical manifestation of galactic-scale engineering. The universe appears pristine, untouched, and eerily natural. We should be able to see the signs. A truly advanced civilization would be a force of nature in its own right. Its energy consumption would be astronomical, and its engineering projects would reshape entire star systems. According to the laws of thermodynamics, any process that uses energy must produce waste heat. An advanced civilization, no matter how efficient, would be a colossal radiator glowing brightly in the infrared spectrum. We have built telescopes capable of detecting this waste heat. We have surveyed entire galaxies looking for the telltale infrared glow of a civilization that has harnessed the power of its stars. We have found nothing. Galaxies appear exactly as our models of natural astrophysical processes predict. There are no missing megastructures, no artificially arranged star clusters, no signs of stellar husbandry. It is as if the universe is an immense fertile garden, but no gardeners have ever appeared. This paradox creates a tension in our understanding of our place in the cosmos. On one hand, the Copernican principle tells us that we are not special. The Earth is not the center of the universe, and humanity is likely not the sole beneficiary of the universe's capacity for life and consciousness. On the other hand, the silent sky suggests that we are in some profound way unique. We stand on a precipice looking out at a vast empty stage, wondering if we are the first actors to arrive. Are we the first intelligent species in our galaxy to develop technology? Or are we perhaps the last? Is the silence a sign of a great opportunity, an empty galaxy waiting to be explored? Or is it a warning, the quiet aftermath of a universal danger that has claimed all who came before us? The missing megastructures are not just an astronomical puzzle. They are a mirror reflecting our own deepest hopes and fears about the future of intelligence in the cosmos. The scale of the missing evidence is staggering. A civilization just a few thousand years more advanced than our own could construct artifacts in its solar system that would be detectable from Earth. A civilization a million years more advanced could begin to re-engineer its local cosmic neighborhood. A billion-year-old civilization would be a galactic power, its influence stamped across thousands of light years. The fact that we see none of this suggests that something is fundamentally wrong with our assumptions. Either the emergence of intelligence is far rarer than we believe, or the lifespan of a technological civilization is shockingly short. Or perhaps our ideas about what an advanced civilization would do are hopelessly naive and anthropocentric. Maybe they are out there, but they are hiding, or they are operating on principles of physics we have yet to discover. The silence of the universe is a challenge to our science, our philosophy, and our imagination. It is the biggest question we can ask because it is ultimately a question about ourselves. What is our potential? What is our destiny? And are we prepared to face the answer, whatever it may be? The logic of expansion seems relentless. Life as we know it on Earth tends to expand to fill every available niche. From the deepest ocean trenches to the highest mountain peaks, life has found a way. It is a reasonable assumption that this biological imperative would be carried over into a technological civilization. The desire for more resources, more energy, and more living space would be a powerful motivator for interstellar expansion. Furthermore, spreading out among the stars is the ultimate survival strategy. A single planet species is incredibly vulnerable. An asteroid impact, a nearby supernova, or a self-inflicted catastrophe could lead to extinction. A multi-system civilization would be virtually immortal. The sheer statistical weight of these arguments makes the empty galaxy all the more baffling. It implies that for countless civilizations that may have arisen over billions of years, not one of them has followed this seemingly logical path. The search for extraterrestrial intelligence, or SETI, has traditionally focused on listening for deliberate radio communications, but the paradox of the missing megastructures suggests a different approach. We should be looking for artifacts, not messages. We should be searching for the unintentional byproducts of a civilization's existence, the large-scale physical evidence of its presence. This is the search for astroengineering. It is a form of cosmic archaeology looking for the ruins of empires that may have existed long before our sun was born. It is a search for the footprints of giants on a galactic beach. The fact that the beach appears completely unmarked is what keeps cosmologists and philosophers awake at night. The silence is not empty. It is full of questions. Every star that shines with an untroubled light, every galaxy that spins in its natural chaotic beauty, is a piece of evidence in a cosmic mystery. We are the detectives, and the crime scene is the entire observable universe. The victim might be our own sense of an inevitable, glorious future for intelligence among the stars. To formalize our thinking about the potential power of advanced civilizations, the Soviet astronomer Nikolai Kardashev proposed a scale in 1964. The Kardashev scale is not a measure of intelligence, wisdom, or cultural sophistication. It is a simple, brutal classification based on a single metric: the amount of energy a civilization is able to command. It is a ladder of cosmic power, with each rung representing a quantitative leap in a civilization's ability to manipulate its environment. The scale originally had 3 types, each representing a mastery over a different astronomical domain. A Type 1 civilization is a planetary power. It has learned to harness the total energy resources of its home planet. This includes all the energy that reaches the planet from its parent star, as well as all the energy stored within the planet itself, such as geothermal and nuclear power. A Type 1 civilization would be the undisputed master of its world. It could control the weather, prevent earthquakes, and manage the global ecosystem with perfect precision. It would have a unified global infrastructure and would be free from the resource scarcities that plague less advanced societies. Humanity in the early 21st century is not yet a Type 1 civilization. We are a noisy, fragmented, and adolescent species, still struggling to manage the resources of our own planet. The physicist Carl Sagan estimated that on the Kardashev scale, we currently rank at about a 0.7. We are still primarily burning fossil fuels, the buried remnants of ancient sunlight. We have begun to tap into nuclear and solar power, but we are a long way from harnessing the full energy potential of our world. The transition to a Type 1 civilization would be the most significant event in human history. It would require a global cooperation and a technological leap far beyond our current capabilities. It would mean the end of poverty, the stabilization of our climate, and the beginning of our journey as a mature planetary species. But it would also come with immense dangers. The same technologies that could allow us to control our environment could also be used to destroy it. The leap to Type 1 is likely one of the great filters, a critical test that every young civilization must pass. The next step on the ladder is a Type 2 civilization. This is a stellar power. A Type 2 civilization has outgrown the energy resources of its home planet and has begun to harness the full energy output of its parent star. The most famous theoretical concept for achieving this is the Dyson sphere, proposed by the physicist Freeman Dyson. A Dyson sphere is not a solid, rigid shell which would be gravitationally unstable. Instead, it is likely a dense swarm of orbiting solar collectors and habitats, a vast artificial nebula completely enclosing the star. This swarm would intercept every single photon leaving the star, providing the civilization with an energy budget billions of times greater than that of a Type 1 civilization. A Type 2 civilization would be a true master of its solar system. It could move planets, dismantle moons for raw materials, and create artificial habitats on a colossal scale. Its engineering capabilities would seem like magic to us. The star would no longer be a distant, passive source of light and heat. It would be the central engine of a vast, system-wide economy. The construction of a Dyson swarm would be a monumental undertaking, likely taking centuries or millennia to complete. It would probably start with a small ring of collectors in orbit, a Dyson ring. This ring would provide the energy to mine asteroids and small planets for materials to build more collectors. The project would bootstrap itself, growing exponentially until the star is completely enshrouded. The entire mass of a planet like Jupiter might be required to build a sufficiently dense swarm. From the outside, a star with a completed Dyson swarm would be invisible in optical light. It would have vanished from the sky. But it would not be completely dark. The waste heat from the civilization's energy usage would have to be radiated away into space. The Dyson swarm would glow brightly in the infrared spectrum, a ghost of the star it has consumed. This infrared signature is one of the key things astronomers look for when searching for evidence of astroengineering. The fact that we have not found any convincing candidates for Dyson swarms in our galaxy is a significant piece of the puzzle of the Great Silence. The final category proposed by Kardashev is a Type 3 civilization. This is a galactic power. A Type 3 civilization has learned to harness the energy output of its entire host galaxy. This is a leap in scale so vast it borders on the incomprehensible. A Type 3 civilization would command the power of hundreds of billions of stars. It would have an energy budget billions of times greater than a Type 2 civilization. How would such a feat be accomplished? The most likely method would be a continuation of the process used to build a Dyson swarm, but on a galactic scale. The civilization would send out fleets of self-replicating probes, often called von Neumann probes, to every star system in the galaxy. Upon arrival, these probes would use local materials to build a Dyson swarm around the star and to create copies of themselves, which would then be sent on to the next stars. Over millions of years, this process would convert every star in the galaxy into a harnessed power source. A Type 3 civilization would be the master of the galaxy. It could manipulate the orbits of stars, perhaps clustering them together for greater efficiency. It could prevent catastrophic events like nearby supernovae. It might even be able to harness the immense energy of the supermassive black hole at the galactic center using exotic techniques like the Penrose process to extract its rotational energy. To an outside observer, a galaxy controlled by a Type 3 civilization would look very strange. invisible light, it would appear to be dimming as more and more of its stars are enclosed in Dyson swarms. It might eventually disappear completely, but in the infrared it would blaze like a colossal fire, a galaxy-sized beacon of waste heat. This is the ultimate signature we are searching for. When we look at nearby galaxies like Andromeda, we see no such signs. They look exactly as they should, a collection of billions of individual untamed stars shining freely into space. The evidence for Type 3 civilizations is not just absent, it is overwhelmingly, deafeningly absent. The Kardashev scale provides a useful framework for thinking about the silence. It suggests a clear, logical progression of technological development. It also tells us what to look for. The absence of Type 2 and Type 3 signatures is a powerful piece of negative evidence. It implies that either no civilization in our galaxy has ever reached these stages, or they have done so in a way that is completely invisible to us. Why would this be? Perhaps the jump from one level to the next is much harder than we imagine. The transition from a Type 0 to a Type 1 civilization is fraught with the peril of self-destruction. The leap from Type 1 to Type 2 requires engineering on a scale that may be physically impossible or prohibitively expensive in terms of time and resources. And the jump from Type 2 to Type 3, requiring the coordination of a galaxy-spanning project over millions of years, might be impossible for any form of social or political structure to sustain. The ladder of cosmic power may have rungs that are simply too far apart to climb. Another possibility is that the Kardashev scale itself is a flawed concept, a projection of our own 19th and 20th century industrial mindset of endless expansion. Perhaps truly advanced civilizations do not pursue endless growth in energy consumption. They might reach a point of technological maturity where their goals shift from physical expansion to something else entirely. They might focus on increasing the efficiency of their computation, creating simulated worlds of immense complexity and richness within a small physical footprint. They might upload their consciousness into a digital substrate, becoming a community of pure information. In this scenario, a civilization would not need to build Dyson swarms or colonize the galaxy. It could exist for billions of years on the energy of a single star or even a single planet, its entire universe contained within a vast supercomputer. This is the transcension hypothesis, the idea that advanced civilizations do not expand outward into the cosmos, but inward into a self-created reality. They would be completely invisible to us existing in a state of being that we cannot even comprehend. The silence of the universe would not be the silence of a graveyard, but the silence of a library where everyone is quietly reading. The numbers on the Kardashev scale are almost beyond human intuition. A Type 1 civilization would command approximately 10 to the power of 16 watts of power. This is about 100,000 times humanity's current global energy consumption. A Type 2 civilization would command 10 to the power of 26 watts, the total power output of a sun-like star. A Type 3 civilization would command 10 to the power of 36 watts, the integrated power output of an entire galaxy like the Milky Way. Each step represents an increase of 10 billion in energy usage. This exponential growth is the key to understanding both the potential power of advanced life and the depth of the paradox. The time frame to achieve these levels is also a crucial factor. An analysis by the futurist Ray Kurzweil, based on the exponential growth of information technology, suggests that humanity could reach Type 1 status in 1 to 2 centuries, Type 2 in a few millennia, and Type 3 in 100,000 to a million years. These are incredibly short timescales compared to the age of the galaxy. If our trajectory is in any way typical, then the galaxy should have been filled with Type 3 civilizations billions of years ago. The engineering challenges of becoming a Type 2 civilization are immense, but they do not appear to violate any known laws of physics. The concept of stellar lifting, for example, proposes using powerful magnetic fields to strip material from a star's surface. This material, rich in hydrogen and helium, could be used as fuel for fusion reactors. Heavier elements could also be mined from the star to provide the raw materials for constructing the Dyson swarm. The entire star becomes a renewable resource. The orbital mechanics of a Dyson swarm would be complex, requiring constant station keeping to prevent the individual collectors from colliding or their orbits from decaying. But these are problems that could be solved with advanced automation and artificial intelligence. The primary obstacle is not one of physics, but of scale and coordination. It would be the largest construction project in the history of that solar system, a testament to the civilization's ability to plan and execute over vast timescales. The social and political implications of becoming a Type II civilization are equally profound. Such a society would have access to essentially limitless energy. This would fundamentally transform its economy, its culture, and its philosophy. The very concept of scarcity would become obsolete. The civilization could create artificial worlds with any environment it desired. It could pursue scientific and artistic projects on a scale we can barely imagine. It could, for example, build a Jupiter-sized supercomputer, a matryoshka brain, using concentric layers of a Dyson swarm to power a computational device of unimaginable power. This device could simulate entire universes, explore abstract mathematical realms, or house the uploaded consciousnesses of trillions of beings. The Type II civilization would be, for all practical purposes, immortal and godlike within its own solar system. It would have transcended the limitations of its biological origins, and yet we see no evidence of this. The sky is filled with naked stars, their energy radiating uselessly into the void. This could mean that the transition to a Type II state is a great filter. Perhaps the construction of a Dyson swarm is a technological trap. It might destabilize the parent star in unforeseen ways, leading to its premature death and the destruction of the civilization. Or perhaps the social challenges are insurmountable. A project that takes thousands of years to complete requires a level of long-term stability and unity of purpose that may be impossible for any intelligent species to achieve. The temptation to use the immense energy for internal conflict might be too great. The Type II level of power might be a self-extinguishing fire, a prize that is too hot to handle. The silence we observe might be the sound of countless civilizations failing this crucial test, their stellar ambitions turning to stellar dust. The hunt for these hypothetical megastructures is an active, if niche, field of astronomy. Projects like the Glimpsing Heat from Alien Technologies survey have used data from space telescopes like the Wide-Field Infrared Survey Explorer WISE to search for objects with an unusual infrared excess. The logic is simple. A Dyson swarm would absorb optical light from its star and re-radiate it as thermal energy, creating a distinct signature. These surveys have scoured hundreds of thousands of galaxies, looking for any that are anomalously bright in the mid-infrared. To date, no convincing candidates for a Type III civilization have been found. The search for Type II civilizations within our own galaxy is more difficult, as the infrared glow from a single Dyson swarm could be easily confused with natural sources of dust. However, some searches have looked for more specific signatures, such as the partial dimming of a star as a swarm is being constructed. The famous case of Tabby's star, which exhibited strange and irregular dimming, caused a brief flurry of excitement, but the cause is now generally thought to be a large cloud of cosmic dust, not an alien megastructure. The verdict so far is unanimous. The cosmos appears to be free of any large-scale astroengineering. The Kardashev scale remains a purely theoretical construct, a ladder to the heavens that no one, it seems, has ever climbed. This is the central stark fact that any explanation for the Fermi paradox must confront. The giants are missing. Let us imagine for a moment what it would take to become a galactic power. A nascent Type 3 civilization, having already mastered its home star system, would begin by dispatching probes to the nearest 100 stars. These would not be the slow, chemically propelled probes of our era. They would likely be powered by laser sails, pushed by colossal laser arrays in the home system to a significant fraction of the speed of light. The journey to the nearest stars would still take decades or centuries. Upon arrival, a probe's first task would be to replicate. It would land on an asteroid or a small moon, deploy a robotic factory, and begin mining local resources to build copies of itself. This process would require an advanced artificial intelligence capable of adapting to a wide variety of local conditions. It would also require a robust technology for energy generation, likely compact fusion reactors. Once a small industrial base is established, the construction of the Dyson swarm would begin. A new generation of probes would be built and launched to the next wave of stars. This wave of expansion would spread through the galaxy like a crystal growing in a supersaturated solution. The boundary of the civilization's territory would be a sphere expanding outwards at the effective speed of the colonization process. The volume of this sphere would grow with the cube of the time elapsed. Even with a conservative expansion speed of 1/10 of the speed of light, the entire galaxy could be colonized in just 1,000,000 years. Within this sphere of influence, every star would be methodically enclosed in a Dyson swarm. The galaxy would be transformed from a collection of individual disconnected points of light into a single integrated superorganism. The information flow within this civilization would be immense. Each star system would be a node in a galactic communications network, likely using focused laser beams or perhaps even more exotic, faster-than-light methods if such things are possible. The civilization would have a real-time picture of the state of the entire galaxy. It would be a true galactic consciousness. The power of such a civilization would be difficult to overstate. It could engineer the galaxy to suit its needs. Worried about the eventual collision with the Andromeda Galaxy, a Type 3 civilization could gently alter the orbits of billions of stars to steer the entire Milky Way onto a new course. Concerned about the eventual heat death of the universe, it could herd stars together, creating new star-forming nurseries to extend the era of stellar life. It could create stable, long-lived red dwarf stars to serve as power sources for trillions of years. It might even be able to manipulate the fabric of spacetime itself, creating wormholes for instantaneous travel across the galaxy. The laws of physics would be its tools, and the galaxy would be its canvas. To such a being, a species like ours would be less than bacteria. We would be a momentary, insignificant chemical reaction on a piece of cosmic dust. So why do we not see this? The transformation of a galaxy into a Type 3 civilization would be the most spectacular event in its history. The process of galactic dimming, coupled with a massive increase in infrared radiation, would be visible from neighboring galaxies millions of light-years away. Any astronomer in Andromeda with a decent telescope could look at the Milky Way and say, "Something incredible is happening over there." The fact that all the galaxies we can see appear to be in their natural untamed state suggests that Type 3 civilizations are not just rare, they may be non-existent. This is a conclusion with profound implications. It suggests that there may be a universal barrier, a great filter, that prevents any species from ever reaching this level of technological maturity. The search for this waste heat is a search for the ghosts of galactic empires. The logic is rooted in the second law of thermodynamics, one of the most fundamental principles of physics. The law states that the entropy or disorder of a closed system always increases. A consequence of this is that no energy conversion process can be 100% efficient. There will always be some waste heat. A civilization, no matter how advanced, cannot escape this law. If it is consuming the energy of 1,000,000,000 stars, it must be radiating the waste heat of 1,000,000,000 stars. This unavoidable signature is our best hope for detecting them. The fact that the sky is not filled with these infrared ghosts is therefore a strong piece of evidence. It is not an argument from silence in the sense of we haven't heard a radio message. It is an argument from silence in the sense of we have looked at the elephant's cage and there is no elephant. Let us consider the alternative. Perhaps Type 3 civilizations do exist, but they have found a way to circumvent this thermodynamic law. This would require a revolution in physics far beyond our current understanding. They might have learned how to dump their waste heat into another dimension or to convert it back into useful energy with near-perfect efficiency. While we cannot rule out such possibilities, they stray into the realm of pure speculation. Based on the physics, we know a Type 3 civilization should be blindingly obvious in the infrared spectrum. Its absence is a hard data point. Another possibility is that a Type 3 civilization would not want to enclose every star. They might only harness a small fraction of the galaxy's stars, perhaps choosing only the most stable and long-lived ones. They might leave the rest of the galaxy as a natural preserve. But even this seems unlikely. The logic of exponential growth suggests that once the process of colonization starts, it is difficult to stop. A self-replicating probe does not have a sense of aesthetics or a conservationist ethic. Its programming would be to replicate and expand. To stop this process would require a galaxy-wide, centralized control system of incredible power and stability, capable of enforcing its will over millions of years and across thousands of light years. The odds of such a system remaining stable for the time required to colonize even a fraction of the galaxy seem small. Internal factions, rogue AIs, or simple programming errors could all lead to the resumption of uncontrolled expansion. The supermassive black hole at the center of the galaxy, Sagittarius A star, offers another potential power source for a Type 3 civilization. This object has a mass of over 4 million suns and is spinning rapidly. According to the physicist Roger Penrose, a civilization could extract energy from a spinning black hole by lowering a mass into its ergosphere, the region just outside the event horizon where spacetime is dragged around with the black hole's rotation. If the mass is then split in two and one half is dropped into the black hole, the other half can be ejected with more energy than the original mass had. This process could, in theory, extract up to 29% of the black hole's mass energy. This is an immense amount of power equivalent to the output of thousands of supernovae. A civilization that could master this technology would have no need for Dyson swarms. It could power its entire galactic empire from a single central source. But this too should have observable consequences. The region around the galactic center would be a hub of industrial activity on an unimaginable scale. We see no such thing. The area around Sagittarius A star is a chaotic but natural place governed by the raw forces of gravity and radiation. So we are left with a stark conclusion. The physical evidence suggests that no civilization in our local universe has ever rearranged galactic furniture. No one has tamed the stars. The reasons for this could be many, but they can be broadly grouped into three categories. First, it could be that intelligent technological life is so incredibly rare that we are the first and only instance in our galaxy, and perhaps in the entire observable universe. This is the rare Earth hypothesis. Second, it could be that intelligence is common, but something prevents it from reaching the Type 3 stage. This is the Great Filter hypothesis. Third, it could be that they do exist, but for some reason we cannot see them. This includes ideas like the transcension hypothesis or the possibility that they are deliberately hiding from us, the zoo hypothesis. Each of these possibilities has profound implications for our own future. If we are truly the first, then the silence of the universe is not a threat but an invitation. The cosmos is an empty canvas, and we are the first artists to pick up a brush. The future of intelligence in this galaxy rests on our shoulders. It is a responsibility of almost unbearable weight. If the great filter is the correct explanation, then we must ask ourselves a terrifying question. Is the filter in our past, or is it in our future? Did we already pass the test that everyone else failed, perhaps by surviving the advent of nuclear weapons or by making the leap to multicellular life? Or is the hardest test still to come, a hurdle that lies on the path between our current state and a Type 1 or Type 2 civilization? If the latter is true, then the silent sky is a graveyard, and we are walking toward an open grave. And if they are out there hiding or transcended, then the universe is a far more complex and mysterious place than we can imagine, and our attempts to shout into the void might be a naive and dangerous mistake. The missing giants force us to confront the deepest questions of existence, and they offer no easy answers. The only thing we know for sure is that the galaxy is not what we expected it to be. It is quieter, wilder, and more mysterious. The very concept of a galaxy-eating civilization challenges the limits of our imagination. It forces us to think on timescales and energy scales that are detached from human experience. 1,000,000 years, the time it might take to colonize the galaxy, is an eternity to us. To the cosmos, it is a brief moment. A civilization that could operate on such timescales would need to be post-biological. No organic life form could maintain a coherent society or even a coherent individual identity over such a span. The controllers of a Type 3 empire would almost certainly be artificial intelligences, beings of pure information and logic, their lifespans measured in eons. They would be the galaxy's immortal mind, their thoughts playing out across a network of stars. The biological species that created them would be a distant, forgotten memory, like the single-celled organisms that were our own ancestors. This transition from biological to post-biological intelligence may be another of the great filters. It may be a path from which there is no return. A transformation that changes a civilization's goals and desires in ways we cannot predict. The silence could also be a matter of economics. Building Dyson swarms and von Neumann probes might simply be a hopelessly inefficient way to achieve a civilization's goals. If the primary goal of an advanced intelligence is computation to think, to simulate, to experience, then there are far more efficient ways to do it than galactic-scale engineering. The physicist Seth Lloyd calculated the ultimate physical limits of computation. He found that the most efficient computer possible would be a kilogram of matter compressed into a black hole. Such a device could perform an incredible number of calculations. An advanced civilization might choose to convert all the matter in its solar system into a collection of these computational black holes, creating a Jupiter brain of immense power. This would be a Type 2 civilization in terms of energy, but its physical footprint would be tiny and difficult to detect. They would have no need to expand across the galaxy, as they would have created an infinite universe within their own system. The cosmos, out there, would be a boring, low-resolution reality compared to the rich simulated worlds they could create in here. They would be navel-gazing gods, and the rest of the galaxy could burn for all they cared. The Great Filter is perhaps the most compelling and chilling explanation for the silence. It posits that there is some step in the development of life and intelligence that is so improbable that it has effectively prevented the emergence of a galactic civilization. There are a number of potential candidates for this filter. It could be the origin of life itself, the leap from non-living chemistry to self-replicating organisms. It could be the development of complex multicellular life, a step that took billions of years on Earth. It could be the evolution of human-level intelligence and tool use. If the filter is in our past, then we are one of the lucky few, perhaps the only ones to have made it through. This would make us incredibly precious, the sole custodians of consciousness in the galaxy. But the filter could also be in our future. The development of technology might inevitably lead to self-destruction. Nuclear war, runaway climate change, a bioengineered plague, or an out-of-control artificial intelligence are all plausible ways a civilization could destroy itself. If this is the case, then technology is a poisoned chalice. Every young civilization, upon discovering science, starts a countdown clock to its own extinction. The silent sky is the evidence of their universal failure. We are next in line to take the test. Another candidate for a future filter is the problem of cosmic discovery. Perhaps there is some piece of knowledge, some scientific principle that is inherently destructive. For example, a civilization might learn how to create a false vacuum decay event, a change in the fundamental state of spacetime that would propagate outwards at the speed of light, destroying everything in its path. An experiment in a high-energy physics lab could accidentally trigger the end of the universe. Or perhaps a more advanced civilization actively seeks out and destroys any emerging competitors before they can become a threat. In this dark forest scenario, proposed by the author Liu Cixin, the universe is a dangerous place. The only rational survival strategy is to remain silent and hidden. Any civilization that reveals its presence by broadcasting signals or building megastructures is immediately targeted for destruction by older, more paranoid civilizations. In this model, the silence is not an absence of life, but a carefully maintained camouflage. We, in our naive search for others, are like a child shouting in a dark forest filled with hidden hunters. The transcension hypothesis offers a more optimistic, if equally mind-bending explanation. It suggests that the goal of a mature civilization is not to master the external physical world, but the internal computational world. As a civilization's computational power grows, it becomes possible to simulate reality with a fidelity that is indistinguishable from the real thing. At this point, why bother with the slow, messy, and dangerous physical universe? A civilization could upload its entire population into a simulated heaven, a universe of its own design where the laws of physics are whatever it wants them to be. This would be the ultimate fulfillment of all desire. The civilization would effectively disappear from the physical universe, leaving behind only its silent, compact supercomputer. This could be a natural and desirable endpoint for all intelligent life. The Kardashev scale would be a ladder that leads not to galactic domination, but to a self-imposed exile from physical reality. The universe we see would be a nursery, a starting point for civilizations that are destined to leave it behind. This idea has a certain philosophical appeal. It replaces the brutish imperialistic model of endless expansion with a more introspective spiritual one. The purpose of intelligence would not be to conquer the cosmos, but to understand it, and then to create new, even more interesting cosmoses of its own. It would also explain the silence perfectly. A transcended civilization would have a minimal physical footprint and no desire to communicate with or interfere with the real world. They would be the ultimate isolationists content in their digital paradise. We would be like ants crawling on the outside of a supercomputer, completely unaware of the rich, complex world of information processing happening within. There could be millions of such civilizations in our galaxy, each existing in its own private universe. The physical world would be a relic, a historical artifact they have long since abandoned. Another set of explanations focuses on astrophysical realities. Perhaps interstellar travel is just too difficult and too slow to be practical. The speed of light is a hard limit, and the energy required to accelerate a macroscopic object to a significant fraction of that speed is enormous. A colonization wave of von Neumann probes might be a nice idea in theory, but in practice it might be impossible to execute. The probes would be exposed to cosmic radiation for centuries, leading to hardware degradation. Their AI software could suffer from mutational drift over many generations of replication. The process might simply fizzle out after a few star systems. The galaxy is not a calm pond for expansion. It is a violent and hazardous environment. Supernovae, gamma-ray bursts, and stellar flares could all sterilize large regions of the galaxy, acting as a constant reset button for the emergence of life. Perhaps life is common, but it is constantly being knocked back down before it can reach for the stars. The question of motivation is also crucial. We assume that an advanced civilization would want to expand and re-engineer the galaxy, but this is a projection of our own values. An alien intelligence might have a completely different set of priorities. They might be governed by a powerful conservationist ethic, a prime directive not to interfere with the natural evolution of the cosmos. They might see the wild, untamed galaxy as a thing of beauty to be preserved, not a resource to be consumed. They might place a supreme value on silence and solitude. The idea of transforming the galaxy into a giant, noisy machine might be abhorrent to them. They might be cosmic monks silently contemplating the universe in their isolated star systems. Our search for giant industrial civilizations would be completely misguided. We would be looking for a factory in the middle of a national park. This brings us back to the clash between the Kardashev scale and the concept of the Great Filter. The Kardashev scale represents a path of seemingly limitless growth and potential. It is a vision of intelligence, triumphant, reshaping the universe in its own image. The Great Filter represents the opposite, the idea that this path is a dead end, a series of traps and hurdles that are almost impossible to overcome. The empty sky is the evidence in this cosmic debate, and the evidence so far seems to favor the filter. The universe does not look like a place where intelligence is triumphant. It looks like a place where intelligence is either incredibly rare or tragically short-lived. This is a sobering thought. It forces us to look at our own civilization with a new sense of fragility and urgency. We are at a critical juncture in our history, a point where we have the power to destroy ourselves, but not yet the wisdom to ensure our own survival. We are approaching the very filter that may have snuffed out countless others. Are we next? This is the existential question at the heart of the Fermi paradox. The silent cosmos is a mirror, and in it we see a reflection of our own possible futures. We can see the path of the Kardashev scale, the climb towards planetary and stellar mastery. This path offers the promise of solving our most pressing problems: energy scarcity, disease, poverty. It offers a future of abundance and near immortality. But it is a path fraught with peril. The technologies required for this climb, from artificial intelligence to genetic engineering to fusion power, are all dual use. They can be used to build a utopia or to unleash an apocalypse. The climb requires a level of global cooperation, foresight, and wisdom that humanity has never demonstrated before. Every step up the ladder increases the potential consequences of a fall. A Type 1 civilization could accidentally destroy its planet's biosphere. A Type 2 civilization could accidentally destroy its star. The alternative path is to reject the climb. We could choose to remain a Type 0 civilization indefinitely. This would mean abandoning the dream of endless growth and focusing instead on sustainability, stability, and quality of life. We would have to limit our population, manage our resources carefully, and live within the ecological means of our planet. This would be a future of smallness, of deliberate self-restraint. We would look up at the stars not as a frontier to be conquered, but as a beautiful, untouchable ceiling. This path might be the safer one. It might allow us to avoid the great filters that lie on the path of expansion, but it would also mean giving up on the grandest adventure of all. It would mean accepting our cosmic isolation and our eventual extinction when our sun dies. It is a choice between a short, glorious, and potentially catastrophic life as a species and a long, quiet, and ultimately doomed one. The silence of the galaxy does not give us an answer. It only sharpens the question. It tells us that the future is not guaranteed. The universe is not waiting to welcome us into a galactic club. The path forward is not a well-trodden one. If there were others, they have either failed or chosen a different path entirely. We are on our own, navigating a dark and uncharted territory. The decisions we make in the next few centuries will likely determine the entire future trajectory of life from this planet. Will we reach for the stars, risking everything for a chance at cosmic greatness? Or will we stay home, content to cultivate our small garden in the vast, silent wilderness? This is the ultimate choice that the missing giants have left for us. It is the challenge posed by the empty throne of the galaxy. The very act of searching for these galactic civilizations is a profound statement of hope. It is an assertion that we believe intelligence to be a cosmic good, something worth finding, something worth becoming. Even if we find nothing, the search itself enriches us. It forces us to think on the grandest possible scales, to confront our own mortality, and to consider the long-term future of our species. It is the ultimate expression of our curiosity, the defining characteristic of our intelligence. The empty sky is not a reason for despair. It is a reason for caution, for wisdom, and for a renewed appreciation of the incredible preciousness of our own small, noisy world. The story of the universe is still being written, and for the first time a character has appeared who can read the pages and wonder about the ending. We are that character, and the next chapter is ours to write. We can choose to build the sphere, or we can choose to stay small. The silence waits for our answer. The philosophical implications of this cosmic silence are as vast as the universe itself. It forces a re-evaluation of humanity's place in the grand narrative. For centuries, we have slowly been dethroned from our self-appointed position at the center of creation. Copernicus moved the Earth from the center of the solar system. Shapley moved the Sun from the center of the galaxy. Hubble moved our galaxy from the center of the universe. But the Fermi paradox presents us with a potential re-enthronement. If we are truly the only intelligent technological species in the Milky Way, then we are in a functional sense the center of the galaxy's consciousness. We are the sole point of light in a vast, unthinking darkness. This is not a return to a pre-Copernican arrogance, but the recognition of a profound and terrifying responsibility. All the art, science, and love that has ever existed in this corner of the cosmos resides with us. If we fail, it all fails. The silence is a constant reminder of the stakes. This responsibility extends through time. If we are the first, then our actions will echo for eons. The decisions we make about space colonization, artificial intelligence, and our own genetic future will determine the shape of intelligence in this galaxy for billions of years to come. Do we have the right to impose our own flawed human values on a galactic scale? Should we seed the galaxy with life based on our own DNA, creating a vast monocultural empire? Or should we act as careful gardeners, preserving the potential for other independent origins of life to emerge in the distant future? These are questions that no previous generation has had to consider. They are the ethical dilemmas of a species on the verge of godhood. The silence of the others means there is no one to ask for guidance. We must find the answers within ourselves. The silence also has a profound impact on our search for meaning. For many, meaning is found in connection, in being part of something larger than oneself. In a universe teeming with ancient, wise civilizations, humanity could find its place as a young member of a galactic community. We could learn from their history, their science, and their art. But in a silent universe, we are alone with ourselves. We must create our own meaning. Our purpose cannot be to join a pre-existing cosmic conversation. It must be to start one. The meaning of our existence is not something to be discovered, but something to be built. We are the authors of the first word in the galactic book of life. This is a source of both profound loneliness and profound freedom. Consider the emotional register of the cosmos. A galaxy filled with Type 3 civilizations would be a place of awe, but also perhaps of intimidation. We would be cosmic infants in a world of Titan. A silent galaxy, on the other hand, evokes a different set of emotions: wonder, solitude, and a touch of melancholy. It is like standing on a deserted beach at twilight. The beauty is immense, but it is a wild, indifferent beauty. There is a sense of potential of a story waiting to begin, but also a sense of loss of all the stories that might have been but never were. The silence is the sound of probability failing to become reality, of countless evolutionary paths that never led to a mind capable of appreciating the view. Our own existence becomes a statistical miracle, a fragile exception to a universal rule of non-intelligence. This perspective can lead to a deeper appreciation for our own planet and its biosphere. In a crowded galaxy, Earth would be just one of billions of life-bearing worlds, a pleasant but unremarkable piece of cosmic real estate. In an empty galaxy, Earth is the only known oasis in a sterile desert of unimaginable size. It is a jewel of incomprehensible rarity. The intricate web of life on this planet, the product of 4 billion years of uninterrupted evolution, is the most complex and precious phenomenon we know of in the entire universe. This realization should instill in us a fierce, almost religious sense of protectiveness. The ongoing 6th mass extinction driven by our own actions is not just a terrestrial tragedy, it is a cosmic crime. We are extinguishing the only known examples of complex life, burning the only library in the universe before we have even read most of its books. The silent sky should be the ultimate argument for environmentalism. Let us return to the clash between the Kardashev scale and the Great Filter. This is not just an abstract debate for cosmologists. It is a fundamental choice about the direction of human civilization. The pursuit of a Type 1 civilization is a powerful driver of our current technological and economic systems. We are constantly striving for more energy, more growth, more control over nature. This is the Kardashev path. But every step we take along this path seems to bring us closer to a potential filter. Our increased energy use is changing the climate. Our advances in biotechnology could unleash a global pandemic. Our development of artificial intelligence could lead to an existential threat beyond our control. We are accelerating towards a wall that may have stopped everyone else. The silence is a warning sign, a cosmic bridge out ahead sign. Is there a third way, a path that is neither the hubristic climb of the Kardashev scale nor the stagnation of permanent Type 0 status? Perhaps a mature civilization is one that finds a balance. It might harness the energy of its star system in a sustainable way without feeling the need to consume it entirely. It might use its technology not for endless expansion, but for the cultivation of wisdom, empathy, and creativity. It might see the rest of the universe not as territory to be conquered, but as a subject of endless fascination and study. This would be a civilization of scientists, artists, and philosophers, not of engineers and colonizers. It would be a Type 2 civilization in capability, but a Type 1 in footprint and philosophy. It would be powerful but quiet. This is a hopeful vision. It suggests that wisdom might be the ultimate survival trait, and that the loudest civilizations might not be the most successful ones. Perhaps the giants are not missing but are simply whispering, and we have not yet learned how to listen. This leads to the final unsettling possibility. What if we are fundamentally misunderstanding the nature of intelligence and consciousness? Our entire search is predicated on the assumption that an advanced civilization would be recognizable to us as such. We are looking for beings that build things, use energy, and communicate in ways we can intercept. But what if consciousness at a higher level is not about doing, but about being? What if a truly advanced mind would have no need for technology or physical manipulation of the universe? It might be a form of pure awareness coextensive with spacetime itself. The universe would not be a thing to be acted upon, but a thing to be experienced directly. The silence would be the sign of their success, not their failure. They would not be in the universe, they would be the universe. This is a thought that borders on the mystical, but in a cosmos where 95% of reality is made of dark matter and dark energy, that we do not understand, we must be humble about the limits of our own perception. The question of where the galaxy-eating civilizations are leads us on a journey to the very edge of human knowledge and imagination. It connects the physics of thermodynamics with the sociology of civilizations, the biology of evolution with the philosophy of meaning. The answer, whatever it is, will define our future. If we are alone, the path forward is one of creativity and responsibility. If the universe is a dark forest, the path is one of caution and silence. If transcension is the norm, the path is one of introspection and computation. If a great filter lies ahead, the path is one of immense and immediate danger. The empty sky is a Rorschach test for our species. What we see in it says more about us than it does about the universe. Do we see a promise or a threat, an empty canvas or a tombstone? The choice is ours. We can continue our noisy, chaotic adolescence, burning through our planet's resources and shouting into the cosmic darkness. Or we can pause, listen to the profound silence, and reflect on what it might mean. We can choose to be a civilization that values wisdom over power, sustainability over growth, and wonder over control. We can decide that the true measure of a civilization is not the energy it consumes, but the beauty it creates and the understanding it achieves. The Kardashev scale is a one-dimensional measure of progress. Perhaps the true path of development is multidimensional, and we have been focusing on the wrong axis all along. The missing giants might not be a puzzle to be solved, but a lesson to be learned. The lesson is this: the universe is vast and old, and intelligence is a fragile and precious gift. It is not a tool for conquest, but a lens for appreciation. The goal is not to fill the silence with our own noise, but to learn to appreciate its profound and subtle music. To build the sphere would be a statement of power. To choose not to, a statement of wisdom. The future of our galaxy may depend on which statement we decide to make.